Hi everyone, welcome to Fractional Excitations, the podcast from Tafti Lab at Boston College. The purpose of Fractional Excitations is to discuss the human aspects of research in quantum materials. My name is Enrique Gonzalez, and this is Suleiman Balguri. We are both graduate students from Tafti Lab, and we are joined here today by Nathan Tolva, a senior undergraduate student in Tafti Lab that will be graduating in the following weeks. Now, today he will be talking about his experience and the research that he's been doing throughout the years in Tafti Lab. Hi Nathan, how are you?
Hi Enrique, I'm good.
How are you, Suleiman?
I'm good, I'm doing good.
So Nathan, maybe first you can talk a little bit about how you got into physics and Boston College and eventually into Tafti Lab.
Sure. Yeah, so growing up, I really liked all sorts of pop science things, mostly facilitated by my dad, who has a very similar love of those sorts of things. Watching Cosmos or reading science fiction, things like that, always sort of piqued my interest. And then through high school, I developed a real aptitude for math and science, like in the classroom. And so it sort of felt like a natural coming together of two things that I liked and were pretty good at. So I considered myself kind of lucky going into Boston College, or even applying to school in general. I was pretty set on physics, and I guess I've only gotten stronger in that belief since coming here. So, yeah.
And you mentioned, I wanted to ask you if there are any particular movies, because you mentioned pop science that interested you, but you already mentioned Cosmos. So did you watch the Cosmos of Carl Sagan or Neil deGrasse Tyson?
I watched the Neil deGrasse Tyson.
Oh, I see.
Yeah.
That's the one I watched.
Nice. Yeah.
That's pretty interesting.
Yeah. My dad, though, he watched the Carl Sagan one, so it's like a generational thing. You know?
Okay, that's good.
That's fun.
Let's see if someone else, maybe Nathan, makes a new Cosmos.
Maybe.
So, Nathan, after you got into Boston College, how did you end up in Tafti Lab?
So after my first year, which was a year sort of marked by difficulties due to the COVID-19 pandemic, I wanted to get back in the classroom with physics, but also I wanted a little more out of the lab experimental side of things. There are labs that are tied to the introductory classes, but I wanted to see what it was like in a real lab setting. And I told Professor Tafti this as much when I reached out to him, and I was meeting with him in his office the same week. We were both very eager to get working together, and it was at a time in the lab where there weren't many undergraduate students, and so I think it was a good pairing sort of from day one. We were both excited to start.
I see. And when did you so there are two kinds of physics, right? Experimental and theoretical for our viewers. So how did you decide to try experiments rather than theory?
Yeah, so I also study math as well as physics at Boston College, and as much as I love math, and I'll be the first to admit that I am no prodigy. I struggle, and I like to struggle through it because I like math, but it still doesn't come sort of naturally to me. Not that that's a necessary barrier of entry to something like the theoretical side of physics, but on the other hand, I wanted to be like hands-on with it. I wanted to be in a lab doing, science experiments, something that felt more like what I grew up with my conceptions of physics looking like,
Right, like getting that hands-on view of what you're looking at in the classroom, of what you're learning. Mm-hmm. That is always great. And so, talking about that experience, how was it getting into it? What kind of projects did you get into and eventually do throughout your undergrad? Can you, for all kinds of audiences, explain your research to us?
Yeah, absolutely. So I started basically mimicking the projects of the undergrad student who was teaching me at the time, Andrew Cole. He graduated last year. So I took over a few of his extraneous projects, and as I got better at various synthesis techniques, I was eventually able to work on my own projects under the guidance of a grad student, Elena Streeter, is who I started with, and with her help and with more experience at the lab, I began my biggest project, which was an investigation of a certain class of materials known as thiophosphates. That's thio meaning sulfur and phosphate, so they all have a common structure of P2S6, an anion in their chemical formula. And so by trying different synthesis techniques and trying different starting materials and starting initial conditions, we were able to explore some of the magnetic and thermal properties of these materials. And that's largely been the basis of the last few years of research.
Awesome. Sounds fun.
And you have also done some more on the data analysis side of the things too, right?
Yeah. So a part of the investigation of these materials was the largest part was a collaboration with the Mag Lab in Tallahassee, Florida. We sent some of our samples there to undergo electron paramagnetic resonance measurements, which was a completely new technique to me, both on the experimental side, and then I also took over the data analysis side. So being introduced to that for the first time, while they were my crystals that I grew, and I got to see the data firsthand, it was a fun and very frustrating but very fun and rewarding experience, like working through that and seeing that for the first time.
So you've made these crystals, right? You found a way to fabricate them in the lab, first of all, and then you went on to do these electromagnetic resonance measurements. So can you explain to us a little bit about this measurement and what you're actually getting from it? Because as a physics lab, we're trying to probe into physical phenomena, and of course, and in our lab specifically, we first fabricate materials that could host very interesting phenomena, and then we try to probe them. So in the probing side, in doing this measurement, what can you say about it? How would you explain to us what you are finding here?
So the way I've had it explained to me is that EPR is very good for detecting long-range ferromagnetic interactions. And so when materials are subject to a magnetic field, different materials respond very differently due to the orientation of spins in the lattice. And what we wanted to do was send two materials that had a remarkably different crystal structure. The lattice was very distinct between the two. And we wanted to see how their EPR signals came back, because that way we would be able to compare and contrast with other more well-studied materials who have also undergone EPR measurements, and be able to sort of classify our materials by grouping them with these other more well-studied materials.
Were you able to do this?
Still up for interpretation, I suppose. The family of thiophosphates, they're all van der Waals materials, so they're incredibly thin, and they can be exfoliated to be conceivably as thin as you'd like them. And so they provide a good environment for studying 2D materials. And then going further with that, the silver chromium thiophosphate system specifically has a unique crystal structure that may be a good setting to study spin chains. Because the way the chromium atoms, the magnetic ions in this material, the way the chromium atoms align themselves in this crystal structure, they align themselves in these sort of zigzagging one-dimensional or quasi-one-dimensional chains. And so our big sort of motivation for this project was seeing if we could detect one-dimensional or low-dimensional magnetism in a 2D or quasi-2D crystal structure. And again, whether we were able to do that is up for debate. There are very clear differences between the silver system and then the other system that we sent was a copper system, which has a more triangular sublattice rather than the zigzag sublattice or striped sublattice is what it's typically referred to as. And there are very clear differences between the two, the sort of parameters that we extracted from the data and everything. But we're still working through that.
That's actually nice. But so the major part of MagLab is to use this high magnetic fields. In fact, I was there last December there,
Oh yeah.
and doing those experiments with the high fields to see some changes in Fermi surface.
Mm.
So how will these high magnetic fields help you with your measurements?
Yeah, that's a good question. So the most basic EPR theory states that there's some resonance field in which the resonance absorption occurs, and for at least the materials that I study, the MagLab, they can do both high frequency measurements and high field measurements. And so I think, if I remember right, it was somewhere in 240 gigahertz frequency, and then upwards of 9 Tesla to actually achieve resonance in these materials. And so, as far as I'm aware, I think that's pretty unique to the MagLab is being able to get.
In fact, they spend like a lot of money. Like when we are at the highest field, we will be getting calls from the electricity department.
Oh yeah.
I mean, there will be a control office within the MagLab, and they will be calling us in those walkie-talkies kind of things.
Yeah.
And say, we are at the high field, please do the measurements because it's costing money.
Yeah, it's
like $1,000.
expensive.
It's $1,000 per hour, so that kind of.
Oh wow.
It's pretty expensive when it's in full power.
Yeah.
So you have to waste no time there actually.
Waste no time and can't waste experiments. I think when all was said and done, we had only collected 3 or 4 sort of sets of data from them because that's all the time we had for them.
And who was helping you there?
Hans? Johan Van Tol.
Oh, I see.
He was the one actually conducting the experiments.
Okay. I work with David Krabs.
Okay.
Very nice. Nice. So, after getting this data, I assume there's a lot of data analysis that you have to go through, a lot of coding. How was that experience, and what have you gotten from it?
Sure. So I was a pretty poor coder when I started doing the data analysis. I found the math behind the analysis fairly straightforward, and the actual mathematical sort of framework behind it was things that I had seen before. So the sort of real bottleneck came in coding because I wasn't familiar with like computer logic and things of that nature. And Elena, who I mentioned earlier, was really instrumental in taking time to really sit with me and help teach these skills to me. But I'd be lying if I didn't mention my friends in the computer science department. I'm very fortunate that I live with computer scientists and have many friends in the computer science department. And so, because learning to code is a very much like all encompassing. You know, if someone is teaching you how to code, you need them right next to you at all times to ask them a quick question, or most of the time they would tell me to figure it out myself. But it was good to have them there in case I needed them. I made what would probably have been a longer, more painful process less long and less painful.
Having coding friends definitely is one of the most useful things to have, especially in a physics department.
Yeah.
I would say.
And now I pay it forward. I help. I help people.
That's good.
You help them with what?
With coding.
With coding? Oh, okay. You help new students.
Mm-hmm.
That's good.
Nathan, you are in the coming days graduating. Congratulations. Now, what is ahead for Nathan Tolva? What are the future plans? What are your interests right now? looking up for the future?
So I'm still very interested in condensed matter physics broadly. I think the characterization side, if there's two sides to our research, synthesis and characterization, I think I definitely lean more on the characterization side. I took that into consideration when applying to grad school, and this fall I'll be at Dartmouth pursuing my PhD in condensed matter physics. I don't know what I'll be doing quite yet, and I don't have to make a decision for a little while, but there are some really great magnetic resonance labs at Dartmouth, and so that would be if I'd like to continue down that route, it's absolutely available for me there. But who knows? I could wake up tomorrow and have a change of heart for theory. Who knows?
Congratulations! That's great.
Dortmund is a very nice place.
Yeah, I'm very excited nonetheless. Yeah, whatever ends up happening.
You're not going far.
Not too far.
Yeah, I think it should be nice.
Yeah, awesome. So we may see you around.
Yeah.
Oh, I'll be around. Yeah.
That's great.
Great.
Right.
Thank you, Nathan, for joining and sharing your views. It was fun talking to you.
Of course, guys.
Yeah,
Thanks.
thank you.
Thank you.
So, bye everyone.